gives you a break. This is the portion that I was going to do on my own. I think that we should probably do it in class.
Is the same as the force between two current carrying wires.
All right, so
is the same as the force between two current carrying wires.
All right, so I need to do something. Okay, cool. Now let's get back.
Is the same as.
Okay, guys. So when there's current inside the wire, wires are attracted to each other. So the question is why? Is there such a thing as positive current and negative current? When I was in grad school, my dad calls me up and says, "Kenny, you're not going to believe this." He said, "I discovered that there are two types of currents. One of them is positive, the other one is negative." And he had a press conference about it in Turkey. And he's a famous enough medical doctor. So when he had a press conference, people would show up. And I was a little bit mad at him. I said, "Dad, you should have just asked me." He thought that there was two kinds of current, positive and negative. I said, "How'd you come up with that?" He said, "Well, he and his engineering friend, his best friend had 5 different engineering degrees. Somehow they stumbled onto this accidentally. All right, they stumbled onto it, and they noticed that if you run current through wires, they will attract each other. All right, so you know that the opposite charges will attract, right? So does this mean that we have two opposite currents, one positive, the other negative? And is that the reason why you got the attraction? So it's a positive and negative current. So the question is, we know that the negative charges are moving, so that becomes the current. Does this mean that there are also positive charges moving? So that gives you a positive current. All right, so that's going to be our investigation. All right, so this week's lecture, at least this portion of it, is going to be an extension of the last week's lecture. I'll do a quick review. So what do we have? Got the magnets. Each and every single magnet is going to have a north and a south pole. So where do we get the terminology from? We get the terminology from the fact that if you get a magnet, it's suspended through a string. It's always going to line itself up along the direction of the Earth's magnetic field. So the end pointing towards the North Pole is known as the North Pole of a magnet. The end pointing towards the South is going to be known as the South Pole of a magnet. So how do we know that the magnetic field lines start at the North Pole and at the South Pole? Well, because you can trace it. You can map them, right? How do you map them? You map them using a compass. Compass is a magnet on a pivot. It's always going to point in the direction of the magnetic field lines. All right, so magnetic field has zero effect on charges at rest. It's not going to have any effect on the charges moving parallel to the magnetic field lines. Magnetic field is going to cause a deflection of the charges going across the magnetic field lines. You can figure out the direction of the deflection using the right-hand rule number 1. All right, so what is the right-hand rule? The right-hand rule is this rule, which is it's going to give you the direction of the force. The only thing you have to do is line up your thumb in the direction of the velocity vector. So the motion is in this direction. Fingers are lined up in the direction of the magnetic field, and the palm is going to face or open up in the direction of the force, magnetic force. All right, so what else do we have? We have a charged particle moving from top of the page towards the bottom. Magnetic field is from left to right. Using the right-hand rule, line up your thumb in the direction of the velocity vector. Fingers lined up in the direction of the magnetic field, and your palm is going to open up away from the page, which means that the force is going to be coming out of the page. All right, so the current is coming out of the page. All right, so this is based on right-hand rule number 2. I think that's something we will discuss shortly. Line up your thumb in the direction of the current. Your fingers will curl in the direction of the magnetic field. All right, so what else do we have? Earth's magnetic field is going to protect us from charged particles because the magnetic field is going to trap the charged particles. Charged particles going across the magnetic field will become deflected in a circular motion by the magnetic field, right? So which means that they will become trapped by the magnetic field. So they will be driven into the atmosphere at the poles. The formula for the magnetic force acting on a charged particle is this. This is the formula for you guys, the bottom one. So the strength of the magnetic force depends on the magnitude of the charge. The bigger the charge is, the stronger the force is. It's going to depend on the speed. The faster the charge is moving, the larger the force is. Depends on the strength of the magnetic field. The stronger the magnetic field is, the larger the force is. Also depends on the angle between the velocity vector and the external magnetic field. If they are parallel, no force is acting. The force is going to be maximum when the angle is 90 degrees. All right. All right, so this formula is the same as this formula, except now the charges are moving in bunches. Instead of a single charge, you have a current moving along the length of the wire across the magnetic field, just like that. So it's going to experience a magnetic deflection. It's going to experience a magnetic force. All right, so the stronger the current is, once again, the larger the force is going to be. Stronger the magnetic field, larger the force is going to be. Longer the wire is, the length of the wire, stronger the magnetic force is going to be. There's the magnetic moment formula. It's like a magnetization factor. how much a loop is going to act like a magnet. All right, so mu represents the magnetic moment. Stronger the current is, the larger the magnetic moment becomes, larger the surface area, larger the cross-sectional area is, stronger the magnetic moment becomes. Proper unit is the unit for the currents. It's going to be amperes. Area is going to be square meters. All right, so what else do we have? Stronger the current is stronger the magnetic moment. The larger the area, stronger the magnetic moment. And larger the radius, the stronger the magnetic moment. All right, so the magnetic moment is like a magnetization factor. That's what I call it. But it tells you how much the loop is going to behave like a magnet, in essence. Larger the number of turns, larger the magnetic moment becomes. All right, so how's the direction of the magnetic moment determined? Okay, guys, once again, use the right hand. Line up your thumb in the direction of the current, and then just grab the wire. All right, so your fingers will point in the direction of the magnetic moment. So which means that the magnetic moment is going to be coming out of the page. All right, so line up your thumb in the direction of the current. Your fingers will curl in the direction of the magnetic moment. So in this case, the magnetic moment is going to be pointing out of the page. All right, so the formula for the magnetic torque acting on the current carrying wire is going to look like this. So here's the magnetic moment, the magnetization factor, or how much the loop acts like a magnet. And it's going to try to line itself up in the direction of the external magnetic field. If there's an angle, it's going to experience a torque. It's going to experience a rotational torque trying to line itself up in the direction of the external magnetic field. All right, so what else? I decided not to put any emphasis on that one. Not for you guys, it becomes too technical. And it's not necessary for you guys. All right, so what did Ørsted discover? Ørsted discovered that the current caused magnetism. You can figure out the direction of the current using the right-hand rule number 2, according to which you have to line up your thumb in the direction of the current. The fingers will curl in the direction of the magnetic fields. So if the current is coming out of the page, the fingers will curl in the counterclockwise direction. If the current is going into the page, the fingers will curl in the clockwise direction. All right, so how does the electromagnet work? You got a loop of wire. You get a single loop of wire, and then you just wind it up, introduce a number of loops. As a result, what happens, this coil of wire, it's going to behave like a magnet, electromagnet. And then you place something in the middle, which is easily magnetizable, like iron. So you place an iron core right in the middle. You place an iron right in the middle. It becomes magnetized. You reverse the direction of the current. The polarization of the magnet will also get polarized. All right, so is it possible to wipe out credit cards using regular magnets? Not today, it's not that easy. Using an extremely strong magnet, though, you can still wipe them out, obviously. All right. So how's magnetism generated? By atomic particles. Atomic particles act like small magnets. The only thing we have to do is just get their magnetic fields lined up in the same direction. All right, so which means that you have to get the atoms, and you need to get their magnetic dipole moments lined up in the same direction, in essence. All right, so how do we generate the magnetism? By the atomic particles within atoms. What do we have? We got these microscopic current loops by the motion of these charges. Electrons moving about the nucleus will generate these current loops. If there's current, there's going to be magnetism. At the center, we have a nucleus that's positive. It's also spinning on its axis. All right, so the spin motion of these charges will also Okay. Okay, so how does heating destroy magnetism? The heating destroys magnetism because, by definition, heating means the random vibrational or rotational motion of the molecules, which means that the molecules are, atoms and molecules are randomly vibrating and rotating, which means that their dipole moments will be pointing at random directions. As a result, the magnetism is going to either become less or it's going to vanish. All right, so Earth's magnetic field, a bunch of theories that we went over. Surface current is not responsible for it, because if you go by the rotation of the Earth, which would be rotating in this direction, the surface currents would be moving in the same direction because of the motion of the Earth, which means that Earth's magnetic field would be pointing in the opposite direction. It's not the spin of the core, because the spin of the core is, once again, would be spinning in the direction of the rotation of the Earth. The magnetic field would be pointing in the wrong direction. If the core were to spin in the opposite direction, that would be responsible for Earth's magnetic field, but there's no explanation as to why it should be spinning in the opposite direction of the spin of the Earth. There's no justification for it. All right. So which means that what causes the Earth's magnetic field is still an unknown. The closest theory that we have is more than likely the convection current inside the core, not the spin of the core, but the convection currents inside the core. It's just a theory, though. It's not proven, obviously. So what do we know? We know that the Earthstat discovers that the current causes magnetism.
Hans Christian Ørsted discovered that electric currents produce magnetic forces, and that those forces always make magnets point perpendicular to the direction of the current.
All right, so we figured out the direction of this magnetic field using the right-hand rule number 2, according to which you line up your thumb in the direction of the current, the fingers will curl in the direction of the magnetic field. Okay, cool. So that's more or less, we came up with an observation, the Earthstat did, and then we introduced a right-hand rule number 2 because we knew the direction of the magnetic field. How do we know the direction of the magnetic field? Because we can map the magnetic field using a compass. All right, so that's as far as we got. All right, so we don't have a mathematical expression for the strength of the magnetic field as yet, and we will get the mathematical justification for it first from these guys, 2 Frenchmen, Biot and Savard. All right, so this thing is mathematically beyond the scope of this course, so we will just skip that one. Everything is reduced down to this simple formula that you're looking at. So this is the formula that we will get to use to figure out the strength of the magnetic field around a wire. All right, so notice that this is the radial distance. All right, so further away you get from the wire, the weaker it's going to become. All right, so the radius is located here. Here's the strength of the magnetic field. So the strength of the magnetic field is generated by the current is going to depend on the current. All right, so stronger the current is, stronger the magnetic field. And also, it's going to diminish with distance as the radial distance. All right.
Is the same as the force between 2 current carrying wires.
All right, so when we have
Is the same.
when you have current in the wires, they can attract if the currents are in the same direction, and they will repel if the currents are in opposite directions. Okay, so is there such a thing as a positive and negative current? So that's what we are discussing. All right, so if the currents are in the same direction, you end up getting attraction. If currents are in opposite directions, you end up getting... All right, so pick out the best answer. All right, so if they are, okay, so if they are in opposite directions, we will end up getting repulsion, right? If they're in the same direction, we'll get attraction. All right, so the question, all right, guys, this current is going to generate a circulating magnetic field around it, right? So focus on this current. Because of the current, there's going to be a circulating magnetic field. It's going to generate its own magnetic field. And that magnetic field in return is going to act on this wire. All right, so there's going to be a current in this wire under the influence of this external magnetic field. As a result, it's going to experience a force in this direction. So this becomes the right-hand rule number 1. Right-hand rule number 2 explains that the current generates magnetism. This is the direction that the magnetic field is going to be generated. It's going to be looping in the counterclockwise direction around the wire. And this magnetic field acting on this current wire is going to induce a force on it using the right-hand rule number 1. Line up your thumb in the direction of the current, fingers in the direction of the magnetic field. Palm is going to point in the direction of the magnetic force. So it's going to experience a magnetic force in this direction. All right, this current is also going to create its own magnetic field. All right, so you can figure out the direction of the magnetic field using the right-hand rule number 2. So your thumb is in this direction, fingers will curl in this direction. So there's going to be a magnetic field acting on this wire in the downward direction. Line up your thumb in the direction of the current, the fingers lined up in the direction of the magnetic field. Your palm is going to point to the right. Your palm is going to open to the right. So that explains the magnetic force. All right, so when the magnetic forces are in opposite directions, obviously, these wires will be attracted to each other. Okay, well, they're pointing, this is pointing to the right, the other one is pointing to the left. So they are, when they're pointing towards each other, they will be attracted to each other. When they're pointing away from each other, they will be repelled from each other, obviously. All right, so both wires are experiencing magnetic force. So there's no such thing as a negative or positive current per se. Current, by definition, are charges moving in the same direction. And we know today that the charges moving in the same direction are. All right. So mathematically, how does this look like? All right, so here's what we got. Here's the first current wire. There's the second one. The currents are pointing in the same direction, right? In both cases, the currents are pointing out of the page. All right, so the current is pointing out of the page. We're looking at the first wire. Magnetic field is going to be in the counterclockwise direction. All right, so this magnetic field right at that point is going to be in the opposite direction. And the strength of the magnetic field right at that point can be found using this formula that I just came up with. R represents the radial distance to the circle where the magnetic field is, which is the same as the distance between these two wires at this point. All right, so it's the same as the distance between the wires. All right, so this is the mathematical expression for the Oersted discovery, or the second right-hand rule. All right, so using the first right-hand rule, what do we have? So thumb is coming out of the page, the fingers are pointing in the direction of the magnetic field. And then palm is pointing, facing to the right, so magnetic force is going to be to the left. To our left. All right, so this force is going to be this current, the length of the wire, the strength of the magnetic field due to the first current wire, times the sine of the angle between the direction of the current and the magnetic field. Current is coming out of the page, the magnetic field is 90 degrees to it, so which means that this angle is going to be 90. All right, so this is the magnetic field due to the first current loop or wire. All right, so this is going to be 90 degrees. Sine of 90 is going to be 1. That's it. So here's the magnetic force acting on the second wire due to the first wire. That's what it means. All right, so this is the current on the second wire times the length of the wire times the strength of the magnetic field of the first wire, which happens to be this expression. All right, so I'm simplifying it. So mu naught is a constant. We got the length of the wire. And then what else do we have? I1 and I2 divided by 2 pi r. That's it. So this gives you this strength of the force, magnetic force between two wires. All right, so both of them are going to experience the same magnetic force, provided that both of them have the same length. All right, so here's the magnetic field due to the first wire acting on the second wire. It's in the downward direction, which is going to be the same as the first one, except it's going to be pointing in the opposite direction. All right, so I don't want to make it too mathematical. I just want to go over some of the basics. The only thing you have to worry about are the formulas. Okay, so here's what Oersted discovered in 1819 or 20. If there's current causes magnetism, right? This is the formula we'll get to use for that one. All right, so this is the formula that we've been discussing. All right, so the stronger the current is, the stronger the magnetic field. All right, so further away you get from the wire, the weaker the magnetic field is going to become. That's what it means. All right, so if there is a loop of wire, all right, you have a loop of wires, so strength of the magnetic field right at the center is going to be found by this formula. All right, this is the formula for that one. All right, so this time you have a loop of wire, and the magnetic field is just wrapping itself around it, right? So here's the wire loop. So the strength of the magnetic field is going to be found using this formula. Okay, so the difference between this formula and that formula is there's pi missing. This shape requires that you use this formula, and if it's a single wire, linear wire, straight wire like that, the strength of the magnetic field is found using that formula. All right, if you have multiple loops, like a coil, this is known as a solenoid. All right, here's the length of the solenoid. These are the number of turns that you have. So L represents the length of it. N is going to represent the number of turns. So number of turns of wires that you have. We end up using a formula that's going to look like this. So here's the current moving in that direction. So the current causes a circulating magnetic field. So the strength of the magnetic field inside this coil or a solenoid is given by this formula. All of them have something in common. It's mu naught I is always going to be common in all of them. All right, so this is your solenoid. All right, this mu naught is just that constant, just like epsilon naught, in case I forgot to mention it. All right, so this is known as the space permeability constant. So, all right, so if it's a wire just like that, straight wire, here's the strength of the magnetic field. So you got mu naught times I. If it's a loop of wire, this is what you end up using. If you got multiple loops, this is the formula that we end up using. All right, so lowercase n represents the number of turns per unit length. So number of turns per unit length is going to be lowercase n. Capital N is the number of turns that you have. Okay, so we'll have more discussion regarding that. So let's just study these different setups carefully. So you have a solenoid. Solenoid looks like that. So you have a coil, you run a current through it. In this case, the current is moving in this direction. And that's going to have magnetic field just going through it. All right, so there's going to be magnetic field within it. There's going to be magnetic field outside of it. All right, so this represents the current coming out of the page. It represents the current going into the page. We're always interested in the strength of the magnetic field inside. All right, so we're interested in the strength of the magnetic field inside a solenoid. All right, speaking of the strength of the magnetic field inside a solenoid. All right, notice that the strength of the magnetic field inside a solenoid is going to be constant. All right, for a given number of turns per unit length. It only depends on the strength of the current, the amount of current that you put in through the wire. All right, so it depends on the current inside the wire. All right, so the stronger the current is, the stronger the magnetic field. Once you're inside the coil, the strength of the magnetic field will remain constant. That's what it means. All right, so once again, you can figure out the direction of the magnetic field using the right-hand rule. 2, thumb is in the direction of the current. The fingers will curl in the direction of the magnetic field lines. According to the formula, the strength of the magnetic field is constant within the coil, but if you're looking at it carefully, it looks like it's going to be constant only near the center. Within that region, it's going to be constant. All right, the reason why we make the assumption that it's going to be constant within the coil is because we make the assumption that the solenoid is infinitely long. All right, so with that assumption in mind, you can assume that it's going to be constant. If you take a solenoid just like that and then turn it into a donut, it's known as a toroid. All right, so you have a solenoid and then you turn it into a donut. As soon as you turn it into a donut, it turns into a toroid. So the name changes. All right, now we got a bit of an interesting situation here. When you turn it into a toroid, what happens to the strength of the magnetic field within? Is it still constant? Okay, so these green lines represent the strength of the magnetic field. So what happens to the strength of the magnetic field when you turn it into a toroid? All right, so toroid is going to be a donut-shaped solenoid. So here's the strength of the magnetic field within. You got the current running through it. Okay, so we'll get to use the same formula as this one. At initial glance, it looks like the strength of the magnetic field is also going to be constant, except now the number of turns per unit length has to be reinterpreted. So the number of turns per unit length has to be reinterpreted. Also, all right, we'll check to see if this radial distance is going to matter now. All right, so this green line is at a small radius, and the other green line is going to be at a larger radius. So will they both experience the same amount of magnetism? Guys, the number of turns per unit length represents the length. In this case, it's a circular length. The length of a circle is its circumference, right? Which is going to be 2 pi r. All right, so what you're doing in essence, you take mu naught times I and divide by 2 pi r. And notice that these magnetic field lines are going to be at different locations. So the one which is further away from the center is going to be weaker. So inside the toroid, the strength of the magnetic field changes radially. It becomes weaker radially. That's what it means. What's constant inside a solenoid is no longer constant inside a toroid. So the strength of the magnetic field is not constant inside a toroid. It's going to change radially. So there's this inverse relationship. All right, so the strength of the magnetic field inside a loop of wire. All right, so I'm going to skip the details for this one. I gave you the formula for it. The formula for it is located right here. Okay, so it's a single loop of wire right at the center. Is going to be this. All right, so it's going to be mu naught times I divided by 2r. These are known as derivations, obviously. This stuff is for calc-based students. All right, so these formulas come out of derivations. That's what I'm getting at. All right, so this is the formula. If you have a single loop of wire, it's not a solenoid. This is a single loop of wire, literally. And it's generating a magnetic field. The only thing I'm interested in is the strength of the magnetic field right at the center. All right, so the strength of the magnetic field right at the center. Notice that pi is missing in this case. All right, so it depends on the radius. Larger the radius is, the weaker the strength of the magnetic field is going to become. So depending upon the size of the wire. So if it's really, if the radius is really large, the strength of the magnetic field is going to be really weak. It also depends on the current, right? So the stronger the current is, the stronger the magnetic field is going to be. All right, so let's finish up the lecture review for this portion of it. So we are done. All right, so what's the formula representing the relationship between the strength of the magnetic field due to the current? So this is what Ørsted discovered. So this is the formula we use for that. Remember, there's a pi there. So what happens to the strength of the magnetic field as the current increases? If you increase the current, larger the current is, the stronger the magnetic field is going to be around the wire. Further away you get from the wire radially, the weaker the magnetic field is going to become. All right. So what happens to the strength of the magnetic field within a solenoid is the number of turns increase. If you increase the number of turns, all right, so if you increase the number of turns, what happens? All right, I'm talking about me, not that. If you increase the number of turns, all right, okay, so this is evidently decided to talk about it here. All right. Remember epsilon naught, this set of speed limit in terms of how fast the electric field could travel through the vacuum of space. Mu naught does the same thing for magnetic field. It just puts the brakes on somehow. It doesn't let the magnetic field travel instantaneously. All right. So this is epsilon naught is known as space permittivity constant, mu naught known as space permeability constant. All right. So this vacuum of space is going to somehow not going to permit the electric or the magnetic fields to travel at infinite speed. All right. So it puts the speed limit. How or why? Something we will discuss later. All right, so mu naught is just a constant. All right, so here's the formula representing the strength of the magnetic field inside a solenoid. So this is what we use. N represents the number of turns per unit length. So the larger the number of turns per unit length is, the stronger the magnetic field is going to become. Stronger the current is, stronger the magnetic field. All right, so if you increase the number of turns, obviously it's going to increase the strength of the magnetic field. Increase the current, it's going to increase the strength of the magnetic field. All right, so what else? Okay, so formula represents strength of the magnetic field at the center of a circle loop is going to be mu naught times I divided by 2R. All right, so mu naught, what's missing here, pi is going to be missing in this case. All right, so let's do one single problem number 3 from this section. Okay. All right, so the current is going up, and then it's looping around, it's going up again. All right, so let's take a look at the strength of the magnetic field at point C at the center. Okay, so it seems like it's an easy problem, which it is, except you will have 2 magnetic field contributions. This is the straight wire. All right, there's a very little gap here, so I mean, just bring them very close to each other. Make sure that this is like a millimeter gap. It's probably even less than that. Tires aren't going to be close enough. The wires aren't going to be close enough, but they're not going to be touching. That's what we were dealing with. All right, so you got a straight wire, and then you also have a loop. So both of them will have magnetic field contributions. All right, for the straight wire, you end up using the right-hand rule number 2. Line up your thumb in this direction, and your fingers will curl around the wire. So due to this straight wire, the magnetic field is going to be going into the page at the center. And due to the loop, the magnetic field is going to be coming out of the page at the center. All right, so here's what I'm talking about. So here's the problem. All right, so let's draw this out. So it's the same wire. All right, I'm just going to place a little bit of a gap here. So it's the same amount of current just going up, a wire, looping around, and straight wire one more time. So center is going to be located right here. So due to the straight wire, the magnetic field is going to be going into the page. And due to the loop, the magnetic field is going to be coming out of the page. All right, so for the straight wire, it's going to be going into the page. For the loop, it's going to be coming out of the page. All right, so this is the magnetic field due to the straight wire going into the page. And this is the magnetic field because of the loop. It's going to be curving, coming out of the page. All right, so the magnetic field due to the straight wire is going to be, if it's coming out of the page, we will assume that that direction is positive. If it's going into the page, we'll make the assumption that's negative. So the magnetic field due to the circulating current is going to be coming out of the page. This is going to be positive, this is going to be negative. So we can sum them up. So right at the center, due to the circulating loop, all right, a wire, so this is going to be coming out of the page. And due to the straight wire is going to be going into the page. Magnetic field due to a single loop of wire is going to be V naught times I divided by 2R. Do this. Magnetic field due to the straight wire is going to be V naught times I divided by 2 pi R. All right, it's got pi missing. All right, so this one is positive, this one is negative. All right, so I'm factoring out the common terms. All right, so that becomes the formula. The rest of it, just plug the numbers in, which I don't really care for.